Welcome to this scientific lecture on one of the most fascinating phenomena in fluid mechanics, the Giant Capillary Pressure Paradox. Here's the paradox. When you shrink a channel down to micrometers, or even nanometers, something extraordinary happens. These tiny channels generate capillary pressures equivalent to high-pressure industrial pumps, reaching tens to hundreds of atmospheres. A simple microchannel becomes a pressure booster, without any external machinery. It's like a garden hose spontaneously turning into a hydraulic press. Imagine you have a garden hose with normal water pressure, maybe 1 atmosphere. Now imagine shrinking that hose down to microscopic dimensions. Suddenly, without any pumps or external energy, the pressure inside can reach over 100 atmospheres. That's the paradox. To understand this paradox, we need to understand the fundamental physics behind capillary pressure. Let me introduce you to the young-laplace equation. The pressure difference equals gamma times kappa. Here, gamma is the surface tension, and kappa is the curvature of the interface. Surface tension gamma is the energy per unit area at the interface between two fluids. For water and air, it's about 72 millinewtons per meter. Curvature kappa measures how sharply the interface bends. The smaller the radius, the larger the curvature. For a general surface, curvature equals 1 over r1 plus 1 over r2, where r1 and r2 are the principal radii of curvature. Let's consider the simplest case, a spherical droplet or bubble. This gives us beautiful insight into the scaling. For a sphere, the pressure difference equals 2 gamma divided by r. Notice the inverse relationship. As radius r decreases, pressure increases dramatically. Consider a water droplet with radius 1 millimeter. The pressure inside is only about 150 pascals higher than outside. That's negligible, barely noticeable. Now shrink that droplet to 1 micrometer radius. The pressure jumps to 150,000 pascals, which is 1.5 atmospheres. We've increased the pressure by a factor of 1,000, just by shrinking the size by a factor of 1,000. This is the key insight. Pressure scales inversely with size. Divide the radius by 10, and you multiply the pressure by 10. This inverse scaling is what creates the paradox. Let me work through a detailed numerical example using water in air at room temperature. The surface tension of water is 72 times 10 to the negative 3 newtons per meter. Case 1, radius equals 1 millimeter, which is 10 to the negative 3 meters. Delta P equals 2 times 0.072 divided by 10 to the negative 3, which equals 144 pascals. That's only 0.0014 atmospheres, completely negligible. Case 2, radius equals 10 micrometers, which is 10 to the negative 5 meters. Delta P equals 14,400 pascals, which is about 0.14 atmospheres. Now we're starting to see significant pressure. Case 3, radius equals 100 nanometers, which is 10 to the negative 7 meters. Now we're at the nanoscale. Delta P equals 1.44 times 10 to the 6th pascals. Let's convert this to atmospheres. Dividing by standard atmospheric pressure, we get about 14.2 atmospheres. That's enormous pressure from such a tiny structure. Case 4. Let's go even smaller. Radius equals 10 nanometers, which is 10 to the negative 8 meters. The pressure reaches approximately 142 atmospheres. This is comparable to industrial hydraulic systems and high-pressure pumps. Here's a summary table showing how pressure scales with size. Notice the dramatic increase as we go from millimeters to nanometers. You might ask, why do we call this a paradox? After all, the physics is straightforward. The paradox lies in our intuition. Our everyday intuition tells us that smaller things are weaker. A tiny stream of water seems insignificant compared to a large river. But at the microscale, reality is inverted. Smaller channels generate higher pressures. The tiniest structures create the most intense forces per unit area. Let me give you an analogy. Think about an ant lifting many times its own body weight while an elephant cannot. An ant can lift 50 times its body weight. An elephant can barely lift a quarter of its weight. Why? Because strength scales with cross-sectional area, which goes as length squared, while weight scales with volume, which goes as length cubed. Smaller creatures have better strength-to-weight ratios. Similarly, with capillary pressure, the pressure scales inversely with size. surface effects dominate at small scales, while bulk effects dominate at large scales. This creates a regime where microscopic structures have macroscopic power. Now let's consider a more practical geometry, cylindrical channels, like the microfluidic devices used in labs and industry. For a cylindrical capillary, the pressure difference equals 2 gamma cosine theta divided by r. Here, theta is the contact angle, and r is the channel radius. The contact angle theta describes how well the liquid wets the surface. For water on clean glass, theta is nearly 0, so cosine theta is close to 1. The contact angle is measured between the liquid interface and the solid surface. A small contact angle means good wetting. For water on clean glass, theta is approximately 0 degrees, so cosine theta is approximately 1. This maximizes the capillary pressure. Let's calculate the pressure in a practical microchannel. Suppose we have a microfluidic channel with radius 5 micrometers. Radius equals 5 times 10 to the negative 6 meters. Delta P equals 2 times 0.072 divided by 5 times 10 to the negative 6, which equals 800 pascals. That's approximately 0.28 atmospheres. Not huge, but significant for a passive device with no moving parts. Now let's shrink the channel to 500 nanometers radius. That's 10 times smaller. The pressure jumps to approximately 2.8 atmospheres. We've increased the pressure by a factor of 10, just by shrinking the channel by a factor of 10. At 50 nanometers radius, which is approaching molecular dimensions. The pressure reaches approximately 28 atmospheres. This is truly remarkable pressure from a channel thinner than a virus. Now here's a question you should be asking. Where does all this energy come from? We're generating huge pressures without any external pumps. Isn't this violating conservation of energy? The answer is surface energy. When the liquid enters a small channel and wets the walls, the system lowers its total surface energy. This energy is converted into pressure energy. Surface energy equals gamma times area. By wetting the solid surface, the system replaces high-energy liquid-air interface with lower-energy solid-liquid interface. The liquid spontaneously enters the channel, because doing so minimizes the total free energy of the system. The capillary pressure is the driving force for this spontaneous process. The water flows into the channel spontaneously, driven by capillary pressure. No external pump is needed. The channel is the pump. This phenomenon has profound real-world applications across science and technology. In microfluidics, capillary pressure drives fluids through lab-on-a-chip devices for medical diagnostics. No external pumps required, making portable diagnostics possible. Paper microfluidics uses capillary action in porous materials. Pregnancy tests and COVID rapid tests rely on this principle. The liquid flows through the test strip purely by capillary pressure. In petroleum engineering, capillary pressure affects oil recovery from tight rock formations. Understanding these pressures is crucial for extracting oil from nanoporous shale. In biology, trees use capillary pressure in their xylem vessels to pump water from roots to leaves, sometimes over 100 meters high, without any mechanical pump. It's nature's hydraulic system. A tall tree uses capillary pressure in its microscopic xylem vessels to lift water over 100 meters against gravity. This is the same principle we've been discussing, working in nature. Now let's discuss the limits. When does this simple picture break down? At what point do we need to worry about other effects? First limit. At the molecular scale, below about 1 nanometer, the continuum description fails. We need to consider discrete molecular structure and quantum effects. Second limit. If the contact angle is very large, above 90 degrees, the liquid doesn't wet the surface. Capillary pressure becomes negative, actually preventing liquid entry. This is why water beads up on a lotus leaf. Third limit. Our analysis assumes equilibrium. At high flow speeds, dynamic effects like viscous dissipation become important and modify the pressure distribution. Fourth limit. In systems with charged surfaces or ionic solutions, electrostatic forces can dominate over capillary forces, especially at nanoscale dimensions. Let me show you the rigorous mathematical derivation of capillary pressure. This comes from minimizing the free energy of the system. The free energy equals surface energy plus pressure-volume work. F equals gamma A plus PV. At equilibrium, the derivative of free energy with respect to volume equals 0. This gives us gamma times dA over dV plus P equals 0. Therefore, delta P equals negative gamma times dA over dV, which equals gamma kappa. This connects the pressure to the curvature through geometric considerations. For a sphere, area equals 4 pi r squared, volume equals 4/3 pi r cubed. Taking derivatives, dA over dV equals dA over dr divided by dV over dr, which equals 8 pi r over 4 pi r squared, which simplifies to 2 over r. Therefore, delta P equals 2 gamma over r. We've rigorously derived the pressure-radius relationship from first principles. How do we know this is real? Let me describe some classic experiments that verify capillary pressure. The classic capillary rise experiment. Place a thin tube vertically in water. The water rises spontaneously to a height determined by balancing capillary pressure against gravitational pressure. The height h equals 2 gamma cosine theta over ρ gr. Here, ρ is density, and g is gravitational acceleration. For water in a 0.5 millimeter radius tube, the height is approximately 3 centimeters. This is easily measurable and verifies the theory. Here's a diagram of capillary rise. The water climbs up the narrow tube against gravity, reaching a height h that depends inversely on the tube radius. For a 10 micrometer radius tube, the predicted height is approximately 1.5 meters. This dramatic rise in narrow tubes confirms the inverse scaling of capillary pressure with size. For those interested in advanced applications, let me introduce the Kelvin equation, which connects capillary pressure to vapor pressure. The natural log of P over P0 equals gamma Vm over RT times kappa. Here, P is the vapor pressure over a curved surface, P0 is the flat surface vapor pressure, Vm is molar volume, R is the gas constant, and T is temperature. This equation tells us that tiny droplets have higher vapor pressure and therefore evaporate faster than large droplets. This is why fog disappears. The smallest droplets evaporate first. This phenomenon is crucial in atmospheric science for understanding cloud formation and in materials science for understanding nucleation and crystal growth. Let me quantify exactly why we call this a paradox by comparing energy densities. A typical industrial hydraulic pump operates at about 100 atmospheres, which is 10 to the 7th pascals. This requires electric motors, pistons, seals, and significant power input. A 10 nanometer water interface generates about 140 atmospheres, which is 1.4 times 10 to the 7th pascals. This requires absolutely nothing except small size. Here's the comparison. On the left, an industrial pump with all its complexity. On the right, a simple nanochannel generating even higher pressure with no moving parts, no power input, nothing. That's the paradox in a nutshell. Let me summarize the key takeaways from this lecture on the giant capillary pressure paradox. First, pressure scales inversely with size. Delta P is proportional to 1 over R. This inverse scaling is the heart of the paradox. Second, at the nanoscale, pressures exceeding 100 atmospheres are possible from pure capillary effects with no external energy input. Third, the energy comes from minimizing surface free energy. The system spontaneously reconfigures to lower its total surface area. Fourth, applications span microfluidics, biological systems, and materials science. Understanding capillary pressure is essential across disciplines. Fifth, the continuum description is valid until we reach molecular scales or encounter high-speed flows where dynamic effects dominate. Here's a final thought to leave you with. The capillary pressure paradox reveals a fundamental truth about nature. At small scales, surface forces dominate over volume forces. This is why insects can walk on water, why cells have certain shapes, and why nanostructures behave so differently from bulk materials. This shift in dominant forces creates an entirely different physical regime. The micro and nanoscale world operates by different rules than our everyday macroscopic experience. Understanding this fundamental shift unlocks the potential of nanotechnology. By shrinking structures, we don't just make them smaller, we fundamentally change how they interact with their environment. And that brings us back to our original statement. The garden hose becomes a hydraulic press, not through magic, but through the beautiful, inexorable logic of scaling laws and surface physics. Thank you for joining me in exploring the giant capillary pressure paradox.